In this video, we're going to focus our attention on the graphs of antiderivatives, building on what we've seen earlier in the course with the graphs of regular or forward derivatives. We're going to use, to a great extent, the fundamental theorem of calculus as we go through this presentation. The relationship we're going to take advantage of originally, though, is the duality between derivatives and antiderivatives, or integrals. The idea is that we are going to be given a function, little f of x, and we're going to be asked to sketch its antiderivative, capital F of x. That's going to be a new relationship to explore, but what we can fall back on is our earlier study of the derivative of a graph giving us a new function. Usually we were given this function initially and asked to compute the derivative or sketch the derivative. Now we're going to be filling in the blanks working backwards. Why is this relevant or helpful? Well, because sometimes we may not be able to actually get an antiderivative by hand. We may not be able to compute with a formula that we're given. So at least with graphical techniques, we can get something even if the formulas are too complicated to get an exact answer. Let's look at our first example. We have a graph, f of x, and it is this bent shape here. And what we're asked to do is sketch two possible antiderivatives of f of x. So using our notation capital F of x, or recognizing that the derivative of the capital F of x is our little f of x. Well, that, again, switches the role from what we've seen before, but when we've done this relationship in the past, we've had a relationship between the slopes on the original graph or the starting graph and the values on the derivative graph. So what we're doing here is a derivative when we move in that direction, or if we go down this way, it's the antiderivative. So what does that tell us? Well, let's take this first point here. If we look at values on this graph, those should translate into slopes on the graph down here. And so if we have a number of -3, then that means initially, let's start up high here, we'll have a slope of -3. If this is our point 1, and we label this, say, 4 for convenience, then we'd be aiming at this point here. And in fact, we can actually see that even shortly afterwards, when we get to 1, the slope is going to be 4. So we could sketch out not a bad graph here with a slope of 3. That's our first anchor point, slope of -3. And then because the value here is -4, we would be changing slope, and then getting to a slope of -4 when x equals 1. By the time we get to x equals 2, we won't be going down quite as steeply. Again, we'll be going down at a slope of -3 again. In fact, we're quickly running out of the scale here. Let's see if we can sketch the rest of it in. -3 slope, and then by the time we get to 3, this is where it gets interesting. We have a 0 value, 0 here. That means the tangent line, or the instantaneous slope, must be 0. All right. So now we have a point where the slope is 0, lined up with x equals 3, and afterwards we have positive values on this graph. That means we're translating into positive slopes on the graph we're trying to sketch. And that gives us a rough shape of the graph that we're talking about when we talk about the antiderivative, where we say our new capital F of x is an antiderivative or an integral of our little f of x. Notice that we were also asked to sketch two possible antiderivatives. There was nothing magic about this starting point. That was just a point we grabbed out of convenience, knowing a negative value on this pointed to a negative slope on our capital F of x. We could also have started at some other point, and we would get exactly the same shape because we have information about slopes. And the only difference is that these would be shifted up or down with respect to one another. And if you think about how that works, when we integrate something, we get plus c at the end, and it would still be a valid antiderivative. Well, that corresponds to the ability to move these graphs up and down depending on what value of c we had found or used. So there's again a graphical relationship between what we're doing in the formulas and what happens when we just sketch without formulas. All right, that's a good starting point. It helps to reinforce the ideas by a few examples though. So let's continue looking at some further graphs. Let's consider g of x, which is equal to the sine of x graph. And this is a graph that we're pretty familiar with, and we're asked again to sketch two possible antiderivatives of g of x. Same relationships apply. If we integrate with respect to x, that's moving from this graph to this graph. If we differentiate, we're moving from the graph on the bottom to the graph on the top. And as we said before, the values on the graph up top translate to slopes on the graph below. So we pick a starting point. And on that starting point, there's a zero value. Remembering the graph of sine peaks at 1, there's a zero value initially, so there'd be a zero slope initially in what we're trying to sketch here. Then the values go positive, and eventually we reach slope 1 at this point here. So something like this. At this point, we'd have a 45-degree line, slope equals 1. This takes a bit of adjustment, but on this next interval, again, we have positive values, all in this range here, as well as the first part, and that means we still have positive slopes. In fact, we're going to move this out of the way for a moment and recognize that we still have positive slopes going after that until we reach this point here, where that translates to, once again, a slope equals 0, aligned with that point. So we're going to have positive slopes until we hit a 0 value. And then what happens after that? On this next interval, we have negative values. We're always below the axis, and that's going to translate into negative slopes. And we already know from our intuition that when we integrate a sine function, we're going to get something like a cos function. And in fact, that's what we end up getting here. We expect to see the same patterns repeat themselves. This 0 value corresponds perfectly to a 0 slope on this graph. And we would just continue that pattern. All of these 0 values on the little g of x graph translate to 0 slopes on the capital G of x graph, like so. Slope equals 0. And slope equals 0 here as well. That's the basic technique. The landmarks are points of 0 value here correspond to 0 slope when you align them vertically. And in between those points, you see slopes that are consistently some pattern, either all positive, so the graph here is going up, positive slopes, or negative values. That means the slopes are negative. That means the function's decreasing. If we had to sketch another graph of this, we might sketch it like this, just in parallel. Again, we would still maintain those 0 slope moments. Those still have to be aligned with the 0 values on the first graph, but we could shift that whole entire graph up and down without changing the slopes at all. Now there is something a little unsatisfying about this, and that is we don't really know the scale of what's happening over here. We can do the 0 slopes and kind of ballpark the other slopes, but we should be able to do a little bit better, especially when we have the fundamental theorem of calculus at our disposal. The fundamental theorem of calculus is something that tells us on an interval we can compute an area underneath the graph of what we're given, the little f of x, and that's going to lead to a change in the graph that we're trying to sketch. So a quick little barometer here. Let's imagine we have a graph like so, and the area here is equal to 3. Label this point A and this point B, and line these up. Then let's say we started down here at some point, let's say -1. We would again have that relationship that values up on this graph translate to slopes on the graph down here. This is little f of x, this is capital F of x. What can we then say about a sketch? Well, we know at this point here there's a 0 value, so we should have a 0 slope on this graph. We know later on we're also going to have a 0 value, so we'll need a 0 slope later on. But in the meantime, these values are positive, and so that means in the graph we're trying to sketch, we're going to get positive slopes until we line up with B, at which point we get another slope of 0. All right. What's the new feature though? On this interval from A to B, the integral, which is the area under the curve if it's positive, is 3. What we can interpret on this graph is that the vertical distance from here to here, this delta f, is also equal to 3 when we go from A to B. How big is f of b minus how big f of a is? That's the change vertically on the graph here. So that adds another relationship that areas, or more specifically integrals, are going to translate to changes in f, or vertical distances, vertical differences. With that, we can add another layer of detail than we could before, where we were simply looking at values and slopes. Let's see that in the context of our earlier sine graph. In our earlier sketch, we had 0 values, a few 0 values here. That translated to 0 slopes initially, and again, positive values led to positive slopes until we reached this point, which gave us a 0 slope again. And we actually know how the cosine graph works, so we could be a little more precise. We know that what we're going to get is related to the cosine graph. And we know the cosine graph goes up and down, one down this way and one up this way. So in fact, this whole distance here is 2. And we expect to get a cosine graph because we're dealing with a sine graph and derivatives or antiderivatives. And what does that tell us? Find the area beneath one arch of the sine graph. Well, if that's the area we're talking about, that area is going to equal the change in f from here to here. Well, that change in f on that one arch is going to equal exactly 2. So, as a surprise event, under the sine graph, which is a pretty complicated function, under one arch, we are going to get exactly the area 2, and then we could actually compute it on the next interval. The area, more the integral value, on the next arch would be equal to -2. Negative because it's underneath the axis, but still 2 because it would be exactly the same size as the original arch. So that gives us a powerful connection between the areas and the changes in f on the graph down here, and really ties the integrals back to changes in the underlying function in our antiderivative. And just for consistency here, we should be calling these delta g, my apologies, for this particular example. So that's it. If you can connect values on the graph that we're starting with, and then trying to build an antiderivative, you'll see those values as slopes. And if you see areas or integral values, because they can be negative, those will translate to changes vertically on this graph here, or as a short form, delta F or delta G in this case here, big G and big F. With those two relationships, you can pretty much sketch any antiderivative you like. It's a very powerful combination of tools.